Welcome you all to Meki Study Circle channel. In this video, we shall see how to determine the heat generated and compute the temperature distribution within the furnace wall that is made up of silica and the magnesia bricks. We can treat this furnace wall as a composite wall because it is made up of two different materials. We shall solve the problem using both the ANSYS approach and as well as the analytical approach. Moving on to the problem statement. So here this depicts the composite wall, that is the wall of the furnace. The furnace wall is made up of two different materials, that is the silica brick and the magnesia brick. There exists a small gap between the two surfaces and this is treated as the contact resistance. As per the problem statement, this is the inner surface of the furnace and this is the outer surface of the furnace. The heat that is produced inside the furnace is convected to the inner wall of the furnace via the convection mode, and the conduction mode of heat transfer takes place from the silica brick to the magnesia brick via the small gap which is having a conductivity of K2. And also the heat that is generated here, that is in the magnesia brick wall, has to be convected to the outer surface. Here we have got the inner temperature of the furnace and also we have got the ambient air temperature, that is the temperature inside the furnace is 820 degrees Celsius, while the ambient air temperature surrounding the furnace wall is 110 degrees Celsius. Now, as per the problem statement, we need to find the heat that is generated inside the furnace of the wall and the heat transfer that takes place across these walls, and also the temperatures at the walls are to be calculated. So the dimensions is, this is 1 mm, this is 10 centimeters. So here we have got the values, that is K1 and K3, but K2 is not given, but we have got the value of the contact resistance as 0.001 meter square degree Celsius per watt, and the heat transfer coefficient through convection is 35 watt per meter square Kelvin. These are the parameters that shall be determined using the analytical method as well as the ANSYS method, that is the heat transfer through the furnace wall, which is given by Q, and also the temperature distribution through the furnace wall. Now let us see how the problem can be solved using the analytical method. So we shall be picking up the formulas from the heat transfer using the Fourier's law of heat conduction, and we shall see how the problem can be solved. So the data given is K1, which is the thermal conductivity of the silica brick, and K3 is the thermal conductivity of the magnesia brick. Using the value of Cr, we shall determine the value of the thermal conductivity of the surface that is between the silica and the magnesia brick. So using this formula, that is the contact resistance is given by the ratio of the length of the surface divided by the thermal conductivity of the surface into the area. On substitution, we get the value of K2 as 1 watt per meter degree Celsius. Now we shall use this particular formula from the heat transfer to get what is the value of the heat generated inside the furnace wall. So the temperature inside the furnace wall is T1 and the temperature outside the furnace wall is T6. So this is the temperature difference, the higher temperature and the lower temperature. And also the first mode of heat transfer is through convection, next via conduction in the magnesia brick. The ratio of the length of the element to the thermal conductivity multiplied by the cross-sectional area is used for the materials which is conducting heat, whereas the surfaces in which the heat is transferred through conduction is calculated by the reciprocal of the heat transfer coefficient multiplied by the cross-sectional area. On substituting these values, we get the rate of heat transfer as 4889.21 watts. So this is the heat that is generated inside the composite wall. Using this parameter, that is Q, we shall find out the individual temperatures, that is T2, T3, T4 and T5. So now let us see how the value of the temperature T2 can be calculated. So since the first mode of heat transfer is through convection, we shall be using this formula, that is the heat transfer is given by H, which is the heat transfer coefficient through convection into the cross-sectional area into the difference of T1 minus T2, that is nothing but the delta T. So Q value is known, H value is known, A is known, T1 is already given in the problem statement. We can compute the value of T2 and we get the value of T2 as 680.30 degrees Celsius. The heat is now transferred from the inner wall of the furnace to the silica brick. And since the mode of heat transfer is through conduction, we shall be using this formula, that is Q is equal to K1 into A1 by L1 into T2 minus T3. So we have already got the value of T2 from the previous step. On substituting the values for K1 and L1, we get the value of T3, which is 354.35 degrees Celsius. Similarly, to determine the value of T4, again the heat is conducted through the contact surface, that is the surface between the silica wall and the magnesia wall, through conduction. So we shall be using the same formula again, but we shall be substituting the value of K2. So here the K2 value is already got by the contact resistance. So on substitution we get the value of the T4 as 349.46 degree Celsius. The mode of heat transfer from the magnesia wall to the outer surface is through convection, and hence we shall be using this formula for calculating the value of T5. So H value is known and A value is known. T6 is already given in the problem statement. On solving, we get T5 is equal to 249.69 degree Celsius. So these are the values of T2, T3, T4 and T5. Now we shall see how the same problem can be solved using the ANSYS APDL. For that, let us begin with selecting the mechanical APDL from the start menu. We shall begin with clearing the log files of the previous session. For that, click File, select Clear and Start New. Till Do Not Read File, click OK, and execute the clean command by telling Yes. So with this, we have cleared the log files of the previous sessions. Now we shall assign a suitable title. Select File, select Change Title and enter the title. Click OK after entering the title. Now save your work. For that, click File and select Save As, and save the file by giving a suitable file name. Right click and select Fit so that the title shall appear in the bottom left corner of the screen as shown here. Now we shall begin the problem. For that, select Preferences, and here there are no mechanical forces that is acting on the furnace wall, and the furnace wall is subjected only to the temperatures, and hence we shall select the thermal domain, and we shall solve using the H method of interpolation. Click OK. Select preprocessor and select element type, add element, click add, and in this menu select link. And since in the problem statement the mode of heat transfer is through both conduction and convection, we shall be selecting both the conduction and the convection elements. First, let us select the conduction 33 element, click apply. Next, select the convection element 34, convection 34, click OK. So link 33 and link 34 are the elements. Link 33 will deal with the conduction mode of heat transfer, and link 33 element will deal with the convective mode of heat transfer. Now we shall assign the real constants for both the elements, that is the cross-sectional area as given in the problem statement. Select the first element, that is link 33, click OK, and enter the cross-sectional area as given, that is 1 meter square, click OK. Click add and select link 34, tell OK, and enter the cross-sectional area for this element also, which is 1 meter square again. Click OK and close this. So here we have assigned the cross-sectional areas for link 33 and link 34. Click close. Select material properties, material models, thermal, conductivity. So the model number 1 is the silica brick. If I consider, the silica brick is having the thermal conductivity as per the problem statement as 1.5. Click OK. And in between the silica brick and the magnesia brick there is a small contact surface, and we shall assign the thermal conductivity for that material. So click material, select new, and the thermal ID for the second component in the furnace wall is 2. Click OK. And again in thermal conductivity isotropic, enter the thermal conductivity value as 1. Click OK. And next, after the contact surface, we have got the magnesia wall. For that material, new model, and it is given by 3. Click OK. And conductivity isotropic, and enter the conductivity value as given in the problem statement, which is 4.9. Click OK. Now we have entered the thermal conductivity of the silica brick, the contact surface and the magnesia brick. And we have also got the convective mode of heat transfer. For that, select material, new model, and click OK, and here select convection or film coefficient and enter the H value, that is 35 as given in the problem statement. Click OK. So just remember this: 1 is your silica brick, 2 is your contact surface, 3 is the magnesia brick, and 4 is the convection heat transfer coefficient, material exit. So we have defined 4 parameters in the material props. Now after having assigned the values of the thermal conductivities and the heat transfer coefficient, we shall go for creating the furnace wall. So for that, click modeling and select create, and we shall create the model directly using the nodes, and we shall create the nodes in the active coordinate system. For that, select inactive CS. The first node is always the origin. Click apply. Then the second node is at a distance of 1 mm from the origin. Since we have given all the parameters of k and h in meters, we shall assign the dimensions also in meters. So 1 mm is 0.001 meters from the origin. The next key point is at a distance of 0.101 from the origin. Click apply. Next comes the fourth. The fourth node is at a distance of 0.102 meters from the origin. Click apply. The fifth node is at a distance of 0.202 meters from the origin. Click apply. Then the final node is at a distance of 0.03 meters from the origin. So click OK. So now you can see that there are totally 6 nodes that are generated. And since the distance between the node 1 and 2, the node 3 and 4 and 5 and 6 is very small, you can see that as though they are overlapping. But actually they are not overlapping, and this completes the modeling part. The next step is to join these nodes using the line. For that, create under modeling and select elements and element attributes. Now we shall assign the attributes for each node that we have created by connecting those two nodes using the element. The first mode of heat transfer is through convection. So for that, select the convection element that is defined in link 34, that is the number 2, and next select material number. 4 is having the value of h, which is 35, and the real constant set number is 2. In number 2, we have defined the area of cross section for this link 34 element. So select these parameters, link 34, 4 and 2 for convection mode of heat transfer, and select OK. And now go for auto numbered and select through nodes, and we need to pick the nodes. For that, to pick the nodes accurately, since you can see that 1 and 2 is appearing as though they are overlapping, for that go for zoom in option and then pan model right, and keep clicking this until you get the node 1 and so now click the node 1 and 2 until OK. So this is the mode of heat transfer through convection. And next go for element attributes again. The heat is conducted from the inner wall of the silica brick through the mode of conduction. So for that we shall choose the conduction element link 33, and the K value for silica brick is assigned in material number 1. So after selecting these parameters, tell OK. And next again auto numbered through nodes, pick the node 2, and for picking the next node that is 3, go for pan model left and keep clicking this till you get the third node. Pick the node 3 and tell OK. And next go for element attributes again. Again from that select link 33 element again. The material number 2 is having the value of K2. The real constant number is 1, in which we have defined the area of cross section for the link 33 element. So give these attributes for this element 3 to 4. Click OK. Auto numbered through nodes. Select node 3 and 4 till OK. So this part is over. From the contact surface to the magnesia wall. For that, element attributes, the conduction element, and the K3 value is defined in the material number 3, and the constant number 1 is defining the area of cross section for this link 33 element. Click OK. Auto numbered through nodes, pick the node 4 and then click pan model left until you get the node 5 and select the node 5 till OK. And again the mode of heat transfer from the outer surface of the magnesia wall to the outer air is through convection. So for that again go for element attributes, pick the convection element that is link 34, and the H is defined in the material number 4, and select real constant number 2, which is defining the area of cross section for this link 34 element. Click OK. Auto numbered through nodes, select 5, 6 and click OK. So this completes the creation of the model of the furnace wall as per the problem statement. And now go for plot and select multi-plots until fit view. So this is how the wall is generated. So now we shall go for the next step, that is go for solution. Now go for solution, select analysis type. We shall analyze the problem using the steady state heat transfer. Click OK. And now go for defining the loads. Define loads under solution. Click apply. Thermal loads. temperature, and since we have created the model using the nodes, select on nodes and select the first node and assign the value of the temperature, which is 820 degrees Celsius. This is the inner furnace temperature. Click OK. And next, again on nodes, select the outer node, click OK, and assign the value of temperature as 110 degree Celsius, which is the T6 value as given in the problem statement. Click OK. Now you can see that the temperatures are assigned as per the problem statement. Now go for solve and select current LS, click OK, and if you're getting any warning, you can just ignore it and you get the solution is done. Click file and select close. Now go for plot controls, select style, size and shape, and switch on the display of element, click OK. So this is how the wall is generated. For that, let us just keep the model in the oblique view until zoom out. So this is how the composite wall is created, and this is how the temperatures are applied. Now go for general post processor and go for element table, define table, click add and type heat transfer or H trans by sequence number SMISC, click 1, and again 1 because the link 33 and the 34 elements in the ANSYS library SMISC 1 will give the heat transfer value. Click OK, close. Go for plot results, contour plot, element table, H trans, select average, click OK. So you get the value of the heat that is generated, which is 4889.21 watts. So this is almost same as the one that we got in the analytical approach. And now go for nodal solutions, degree of freedom solution, nodal temperature, and click OK. And this is the temperature distribution. So minimum temperature being 110 degrees Celsius and the maximum temperature being 820 degrees Celsius, and these are the intermediate temperatures. And to get the temperatures at each nodes that we have created, go for list results, select nodal solutions, again DOF solution, nodal temperature, click OK. So these are the temperature values that we get. So you can see that in the analytical approach, the heat generated is 4889.2 watts, and similarly in the ANSYS approach also the heat generated is the same, and hence the percentage error is nil. And also the values that we have got in the analytical approach at 2, 3, 4 and 5 nodes is same in both the analytical and the ANSYS approach, and hence the percentage error can be recorded as nil. Now we shall have the model which is depicting the temperature distribution and also the heat generated in the same window. For that, go for plot controls, select multi-window layout and select 2, that is left and right, click OK. So now you can see that the screen is divided into 2 halves, that is the first window and the second window. Go for plot controls, multi-plot controls, and in window 1 select entity plots, click OK, and here select nodal solutions, click OK, and again in DOF solution here select temperature, click OK, right click, fit. So you get this temperature distribution across the composite wall. And in this window we shall have the heat generated. For that, go for plot controls, select multi-plot controls, select window 2 and select element table, click OK, and select heat transfer, yes average, click OK, right click, fit. So you get the model which is depicting the heat transfer, that is 4889.21. Go for plot controls, write meta file, save it as invert white and black and give a suitable file name. Now we can also see the animation of how the heat is flowing from the inner wall of the furnace to the outer wall. For that, go for plot controls, select animate, deformed results, DOF solution, temperature, click OK. So you can see the animation of how the heat is flown from the inner wall of the furnace to the outer wall, and also how the temperature is getting varied across the different nodes of the walls. Click close to end the animation. With this, we have completed the exercise.